Hello, good evening from London. I'm Richard Zhao from Imperial College London. Today, I present our recent work on the challenges in programming mixed precision deep neural networks. I'm currently at my third year of my PhD study and mainly working on deep learning frameworks for hardware accelerators. My past papers basically cover different techniques for efficient deep learning, including mixed precision training, pruning, and hardware accelerated design. If you like, you can find me on Twitter. Recent research shows that DNNs are resilient to low-precision data representation. For example, if we reduce the data type precision of a DNN model from 32-bit single precision floating point to 8-bit integer, the model accuracy may not change, but we can gain much from other perspectives. The memory footprint is smaller, the execution speed is faster, and the power consumption is reduced as well. There are quite a lot of other data types that are proposed to work well with DNN: fixed point, floating point, integer, parset, and binary. Mixing different formats together helps us finding the sweet spot that balances execution performance and the model accuracy. Unfortunately, these low-precision data types can only unleash their full power on customized accelerator. We cannot expect an x86 CPU efficiently processes data types other than floating point and integer. On the other hand, building a hardware that supports such data types takes a long time and costs much money. We cannot risk building a hardware that supports a data type that won't work well for the DNN models we are interested in. Therefore, people will simulate novel data types first to see their performance on DNN baselines. For example, checking how the model accuracy might drop. After that, we can decide whether landing them on a hardware accelerator is a good choice or not. However, sadly, deep learning frameworks, which people normally use to develop DNN models, are not designed for this purpose. There are three possible reasons for why deep learning frameworks are not good enough for mixed precision deep neural networks. First of all, the code base is large and hard to read. Second, modules in the framework are not properly decoupled. Adding a data type may affect many modules. The last but not the least, there is no API exposed for us to create data types. One example from a recent blog post by TVM shows that supporting the deposit data type simulation in TensorFlow is quite a lot of work. In the following discussion, we will use BFlow16 as a target data type to be implemented. BFlow16 can be viewed as a truncated version of a single precision floating point. The 16 least significant bits of flow32 are truncated. Our paper proposes a novel framework named LOGEN, meaning Low Precision Data Type Generator. It is a framework designed to make mixed precision deep learning simpler. LOGEN covers efficient data type generator, JIT compilation, and computation graph optimization. In this presentation, we'll show that what are the specific challenges that LOGEN targets, how are these challenges addressed, and an empirical evaluation that implements BFlow16 by LOGEN. The first challenge is in data type definition. Recall that the data type we want to define is not supported by current CPUs. We should simulate them first by existing types. By saying simulation, we mean that the basic arithmetic operations of the data type to be implemented will be carried out by the simulation data type. Most of the time, the simulation data type is floating point. The figure in the slide shows that how a simulated addition works. tnew is the type we implement, and tsim is the one supported by CPU. We should typecast tnew to tsim first, then perform addition in tsim, and then typecast the result back to tnew. It sounds straightforward, but to implement it with high performance is a challenge. To achieve high performance, researchers should vectorize scalar operators to fully utilize vector processors on widely accessible CPUs. Vectorizing scalar arithmetic operators is easy because vectorized arithmetic operators share a similar pattern. You just need to change the inner simulated arithmetic to its vectorized version. The tricky part is the typecast function. There's no pattern to find among them, as you may notice in the figure on the right. Researchers need to implement vectorized typecast functions by themselves. However, it is not common for researchers who are experts in data types to know all the details about vector processor, instruction set, etc. Writing vectorized code is not in their common skill set. The next challenge is about C++ template. Deep learning frameworks implement their neural network operators as C++ templates. Typically, these templates have two arguments, data type and runtime device. Any new data type should have their own operator template specialization for device. We know that the template specializations statically expand to some code snippet, which will take some space in the compiled object. We notice that specializing all types for all operators is redundant for the specific neural network model. Imagine the model only uses bflow16 for convolution. There's no point to specialize bflow16 for other operators. This causes code bloating. Another problem caused by template is that if we add or change data type definition, we should recompile the whole code base that depends on the operator template specialization. Recompilation takes time and potentially increases research costs. Finally, the last challenge comes from computation graph. A DL model can be represented by a computation graph. Its nodes denote neural network operators and edges represent data flow. The type of a node is the type of its output data. There are typecast nodes in the graph that changes the data type. We introduce them when updating the type of some nodes in the graph to our newly implemented data type. And some of those typecast nodes can be redundant. Redundancy mainly appears around type-agnostic nodes. These nodes will not change model precision when their types are changed. There are two typical redundant cases shown on the right figure. Reshape and concatenate are two types-agnostic nodes. In the first case, the two typecast nodes around the type-agnostic node can be safely removed after we change the type of the reshape to float. For the second case, with the type of concatenate changed to bflow16, moving typecast from the input to the output would be beneficial since there are less typecast node function calls. Our challenge is about how to automatically prevent this kind of redundancy. So far, we've presented three challenges in programming mixed precision DNN in current deep learning frameworks. It is hard for us to provide data type definition with high performance. Operator templates introduce a recompilation burden and code bloating problem. And redundant typecast nodes in mixed precision graph have not yet been addressed. Our framework, Logen, proposes three solutions that address these challenges accordingly. We have vectorized data type generator to generate high-performance code. Logen supports JIT compilation to address the problem around operator template specialization. Moreover, there's a graph optimizer that eliminates redundant typecast nodes. The first Logen module we present is a vectorized data type generator. As mentioned earlier, we should mainly focus on vectorizing the typecast functions. We cannot apply auto-vectorization since the typecast functions don't have a loop structure. However, these typecast functions have good data flow property. Each of them have a single source and a single sink, and if we run a scalar version of multiple continuous input elements simultaneously, the result should be the same as we run in a sequential manner. It suggests that if we replace every scalar instruction with its vectorized counterpart, the function should be turned into a properly working vectorized function. We call this technique instruction mapping. Let's take the bflow16 to float typecast function as an example. The scalar version has three instructions. Typecast from union 16 to union 32, shift 16 bits left, and reinterpret the result as a floating point. We can replace each of them by their vectorized counterpart, and the result is a vectorized version of the original function. The instruction mapping can apply in a one-to-one, one-to-many, many-to-one, or many-to-many manner. We have implemented pattern matches to find the patterns in the scalar version and implemented vectorized instruction templates for them. Based on the instruction mapping technique, we build a code generator pipeline. For each typecast function, we analyze its data flow to ensure it has properly implemented. Then we pass it to instruction mapper. We also generate test and verification code that examine whether the vectorized code can work properly. This pipeline is implemented upon clone. Next, we talk about how JIT compilation can address the recompilation and code bloating problem from operator templates. Our objective is to compile only those template specializations that are in need. Specifically, for a given deep neural network model, we just need to specialize a data type for those operators that are in this type. This can be achieved by analyzing the operator type pairs in a deep neural network model that is currently running. For example, if a model uses BFlow16 for 2D convolution, there should be a pair that is of comp2D and BFlow16. Our JIT compilation makes use of this information to decide whether operator templates should be specialized for which data type. Since this is done in runtime, the operator library size is reduced, and there should be no code bloating. And potentially, when updating the data type definition, we don't need to recompile the whole code base. The JIT compilation pipeline looks like this. We first analyze operator type pairs from input DAN. From this step, we can realize what template specialization should be generated. Then we generate a code snippet that includes the template specialization and compile it to a shared library that can be loaded by Python. We use the CPP import and Python 11 library. The last step is compile the link. Please bear in mind that this JIT compilation technique is not deep learning framework agnostic. It, like list, requires an operator library to be well decoupled from other framework modules. We also need to know how the source code of operator templates look like. The framework should also allow searching for operator implementation from an external Python module. The last Login module is Graph Optimizer. It contains two optimization passes that deals with the two redundant typecast cases we've discovered. For the first tab, we just need to search for the typecast pairs and examine all the passes that connect them. If all the nodes on all the passes are type agnostic, we can remove the typecast node. For the second case, we need to check every type agnostic nodes to see whether it is beneficial to switch the position of typecast from input to output, or vice versa. Benefits are measured by memory usage and the number of function calls. Here we summarize the full workflow of Login. A researcher may define a sketch of a data type, which includes two typecast functions and a storage type. Then our code generator can take it as input and generate a high-performance version of it that leverages vectorized instructions. Now we have a specific DL model workload. We can pass it to the JIT compiler to get a compiled module that contains the specialized operator templates related to the target data type. Also, we can optimize the graph by the mixed precision graph optimizer to get an optimized graph without the redundant typecast nodes. The compile operator module and the optimized module we pass to the DL runtime for further execution. Finally, we present empirical evaluation in Login. We carry out experiments on our in-house TensorFlow-like deep learning framework. The target experiment platform is x86 Intel Xeon CPU. We use Login to implement BFlow16, as mentioned earlier, and our deep neural network baselines cover most computer vision tasks, including classification, object detection, and segmentation. First, regarding BFlow16, compare the performance of Login-generated high-performance data type definition with the baseline implementation. The baseline implementation implements operators at a scalar level, and the version that Login generates uses vectorized instructions. Using Login gives around 8.31 times speedup in average for all DN baselines. UNet here is an anomaly. Its speedup is low mainly because it is a memory-bounded task in our implementation. Also, the lines of code we need to write is reduced as well, since we just need to provide a sketch to Login. Previously, we need to write around 600 lines, but now we just need 30 lines. For the JIT compilation module, we mainly measure the reduction of the object file size. The object file is of the operator library. Without login, we should specialize all operators for bitflow 16. With login, we need to put those bitflow 16 operator specialization that are actually useful for a specific model. The reduction rate on average is 7.30%. We also measure the peak memory usage reduction by using the Mixed Precision Graph Optimizer. Recall that the optimizer can remove redundant typecast nodes. Removing typecast nodes will result in reduced memory usage. SSD and Inception v4 are two models that have many redundant typecast nodes. SSD has many reshaped nodes in it, and there are quite a lot of concatenation operators in Inception v4. Their peak memory usage can be reduced when optimized by login, although the amount of reduction is not significant. We also list the number of reduced typecast nodes as well. Regarding the future work, we are mainly looking at putting the whole workflow of login into Python. We are currently working on implementing an embedded DSL in Python that can define, integrate, and optimize novel data types. There are several motivations. Writing C++ is still tedious, while Python is more familiar to people in the deep learning industry. Based on C++, we cannot easily support different backend devices. However, there are some excellent compilers and DSLs in Python that can generate high-performance backend code. Moreover, using Python provides a seamless experience when developing deep neural network module at the same time. Please keep in touch if you are interested. Here is a summary of our work. We present Login, a framework for simpler mixed precision deep learning. It shows three different challenges we need to face when building mixed precision deep learning models by existing deep learning frameworks, and propose corresponding solutions. The three major modules in Login includes a vectorized data type definition generator, a JIT compilation module for operator template specialization, and a mixed precision graph optimizer. We empirically evaluate the bitflow 16 implementation by Login on various DM baselines. That's all for our presentation. Thanks for attending. Please let me know if you have any follow-up questions.